In this video, I will show you how you can very easily get started with machine learning. And in this series, I will take you from complete beginner to advanced step by step. Today we start simple. First we'll go through setting up your own dataset. Then I'll show you how much you're going to love libraries by setting up a machine learning model with a single line of code. Well, 2 if you include loading the library. The same goes for training, 1 more line of code and we're good. Finally, we'll go through checking the performance of the model. Have we created our new AI overload or a useless, overcomplicated random generator? Let's begin. A good place to start your machine learning journey is with supervised learning. In that case, a dataset will for each entry have some input data and some desired output data called a target. For this series, I will use bird audio as input and species as target. This is then a classification problem, as we have a discrete number of species called classes. For this video, I have collected a small dataset of 226 entries spread across 5 species: the gray heron, the common moorhen, Seti's warbler, the redwing, and the Eurasian coot. You can essentially use anything for a dataset if you follow a few rules. All entries must have the same size. This can be solved with resizing, which is common for images, or padding, which is also common with images, but especially audio or other time series data. I have padded all audio with zeros, so they're all 10 seconds long. For classification, we need to encode the target to some number stuff. In this case, since we'll use sklearn for the model, we can use the label encoder. Then we want to split the data in 2, the data for training and the data for testing. This is so we can see the model's performance on data it has never seen. This gives us an idea of how well its performance generalizes when it's deployed. This is by default a 75-25 split. We also wanted to do a stratified split, meaning preserve the ratio between the classes in both of the new sets. Next, we set up model and training, which often are tightly connected, and in sklearn it is handled by the same object. We will use the MLP classifier. It automatically figures out the input and target sizes, so all we need to worry about are the hidden layers. The default is 1 hidden layer with 100 nodes, but adding layers and changing sizes is as simple as a list of numbers. After each hidden layer, a function called the activation function is applied to each node. This makes it easier for the model to learn complex things. The most popular is the ReLU function, or rectified linear unit, as it often offers the best trade-off between performance and computational load. There are other options though. In training, a batch of data is passed through the model, and from the output, a difference measure between this and the target is calculated. This is called a loss, and this is used to update the model. When all of the data has been passed through, this is called an epoch, and we can limit how many of these we want at max. For now, we'll use all default values except for verbose, as we would like for it to print progress messages during training. And then we ask it to fit the training input to the training targets. We then see it printing which epoch it is in and how big the loss is. There are then 2 different ways training can end: by having not improved by a tolerance for a certain amount of epochs, or by reaching max epochs. If we reach max epochs, we'll get a message saying the model has likely not converged yet, meaning we should increase max epochs. We can also look at the loss and check if the tolerance has a fitting value. Here there are already a bunch of parameters to play around with. Now we arrive at performance validation. We can first plot how the model improves during training with the loss curve. Next we check how well does our model do on previously unseen data. Here we get the accuracy 54%. Is this good? Well, let's do a baseline comparison. The simplest system would just guess for the most common class in the dataset, which is a good time to point out that your dataset should be balanced. For this dataset, that would be 50 out of 226, so about 22% accuracy for the baseline. And our model definitely beats that. But that raises the question of how well it performs for a given class. With a performance of 54%, we might actually have a model that it completely ignores 2 of the 5 classes. This is where the confusion matrix comes in. It has the true data on the y-axis and the predicted data on the x-axis. A perfect model would be a perfect diagonal. We know our model is not quite perfect already, but now we know where it struggles. In this case, when the audio is from the Eurasian coot, it is actually more likely to guess common moorhen. We can also get it as ratios. Needless to say, there is room for improvement, but this is a great start. The next steps are improve the dataset, play around with model parameters, and slowly increase the size. When you get to longer training sessions, maybe you want to train a larger model for longer, improving the training is a good idea. And finally, when you want to show off your amazing model, you want to improve your performance validation so your results are trustworthy. I will make a video about advanced techniques in each of these 4 areas, so be sure to hit like, subscribe, and turn on notifications so we can get your project all professional and shit. Alright, see ya.